Yeah. Oh, you do?
Ahora sí. We are live.
Is she also part of the collective edition stuff?
Esto cuando estás compartiendo es un coñazo.
Right.
No.
Really?
Okay, welcome everyone. Thank you for being here. For the light. Today we have our colloquium speaker from Teruel, Juan Antonio Fernández Ontiveros. I'm very glad he's here because we've known each other for many years now, but we haven't met for years also. Juan did his PhD in the Instituto de Astrofísica de Canarias back in 2010, and then moved to the Max Planck Institute for Radio Astronomy for his first postdoc on infrared interferometry, and went back and forth between the Max Planck in Bonn and INAF in Rome, where he worked a lot on Herschel, also Spica, mostly infrared spectroscopy, until he moved to Teruel, to CEFCA, with a tenure track position in 2021, where he's based right now. So he's going to talk a bit about this infrared expertise he has applied to X-ray binary accretion states in AGN. So thank you, Juan.
Thank you, Mark, for the nice introduction. Thank you for the invitation to give the colloquium here. So today I'm going to talk about accretion states in AGN, and in particular, how can we trace the presence of these accretion states using the nebular lines in the infrared. But first of all, for those of you who doesn't know Teruel, Teruel is somewhere here in the middle between Madrid and Barcelona, and it's actually one of the darkest spots in Europe, and because of the low density of population, and that's why the Observatorio Astrofísico de Javalambre was installed there, no? With the J-PASS survey, which is the main one, with 56 narrowband filters, and now we are releasing the first dataset. 17 square degrees are already published, so if you are interested in this, just talk to me later. Teruel, the city is very nice, very beautiful. It has this mudéjar style, and our PhDs have a lot of fun, but the lazy ones are fed to the T-Rex. So if you want to come to visit these amenities, just let me know. I organize the seminars there, so you are very welcome to come. Now let's move to more serious stuff. The presence, the accretion states were identified for the first time in X-ray binaries, and in particular in low mass X-ray binary systems. We can see these states. So during their lifetime, the systems are formed by a compact object, a neutron star or a black hole, and a companion star. And for most of their lifetime, the companion star transferred mass through the Roche law to the accretion disk of the compact object. This material accumulates, and during this time, the system is in a low state, it's not bright, it's several times below Eddington luminosity. And the material accumulates in the disk until a certain point, thermal instabilities increase the temperature, the opacity, and then a reaction happens when the opacity is increasing, the temperature is increasing, and the system enters into an outburst state. So this is when they are discovered. They are actually the brightest sources in the X-ray sky when they are into outbursts, and that's when they display all the phenomenology that we can compare with AGNs, no, like winds, very high variability, etc. But a better way to identify the states in X-ray binaries is the hardness luminosity diagram. This is basically a representation of the luminosity of the system in X-rays versus the slope, the spectral shape of the X-ray spectrum. When the spectrum is soft, means that the systems are dominated by the emission from the disk. The advantage in X-ray binaries is that their accretion disks are much hotter, so the continuum emission from the disk appears in the X-rays. Then the other side of the figure, during the hard state, in the SED, this means that the inverse Compton emission from the corona or the jet is dominating the continuum emission. And that's why the slope in the X-rays it's harder. So basically, when these systems are in quiescence, they start from here, and then at the beginning of the outburst, the system, it's in the hard state, so it's dominated by this inverse Compton continuum, and its luminosity is increasing during the first few days or weeks. The luminosity is increasing, but the spectrum is still hard, so this has this shape until it reaches a certain point in which the vertical evolution stops, and then the luminosity is kept, but the spectrum becomes increasingly softer. So the disk appears in the spectrum, and the system moves to the left side of this diagram. Then, after some come and go in the left side of the diagram, the system is decreasing little by little in luminosity until again it reaches a certain point where the evolution is again horizontal to the hard state. And that's when the system comes back to quiescence, or it may start a new cycle. So this whole thing may last for 1 year or less. Some systems take longer, some others take shorter time. In any case, the evolution is always counterclockwise. And not all the systems display the full phenomenon. Some systems come here, go, and then go back to quiescence. So, sketch of this cycle, one could interpret the horizontal axis as the relative disk fraction. So systems in the left side of the diagram are dominated by disk emission. Systems of the right side are dominated by corona or jet emission. Two important things is first the morphology that I already discussed. So this hardness luminosity diagram has a Q-like shape. The transitions from hard to soft happen at different luminosities, even for the same system in different outbursts. So the level at which the system starts the horizontal evolution to the left may change from one explosion to another, but the comeback happens always close to 1%. So this limit, it's always the same. This has an implication that if the system is below 1% Eddington, means the system is always in the hard state. So the disk cannot survive below a few percent of the Eddington luminosity. This is when the disk gets truncated and you lose the innermost orbits. This hysteresis diagram is called as well. It's not only seen in the shape of the X-ray spectrum, but it's also seen in the timing properties, in the variability. So this is the fractional amplitude of the fluctuations of the continuum against again the flux or the luminosity for the same system as before, for two different outbursts, one in 2004 and one in 2007. So you can see that the transition from left to right happens at different luminosities, but then from right to left happens at the same. No? And you can identify the same similar Q shape as I was discussing before. Now, moving more to the AGN. So the central point of the talk is about establishing if this phenomenology can be also detected in AGNs. And we know that in AGNs, during the hard state, there is some unification that it's already known, and that's the fundamental plane of black hole accretion. Because this is a relation, a well-known relation between the X-ray, the radio flux, and the black hole mass. So when you normalize, in this case, the X-ray luminosity is normalized by the black hole mass, you can find a common relation from X-ray binaries in the lower left side, Sagittarius A, and low luminosity events, no? And even blazars when you properly correct for BB. So this is a plane that describes how the different how the energy is released in different wavelength ranges when the jet physics is dominating the energy output in these systems. So the question is, can we extend this framework to the whole AGN phenomenology? Are we able to identify the whole hysteresis diagram in AGNs? There are two main difficulties that we have to overcome to answer this question. The first is the very long timescales, which is a problem because we cannot follow the evolution of a system across this whole cycle. In an X-ray binary, it's 1 year. In AGNs, it's millions of years. So we cannot trace the full variability. And the other is the discontinuum. We don't have the discontinuum in the X-rays, but the discontinuum in AGNs is in the optical ultraviolet. And there, absorption by hydrogen is very heavy and removes most of the discontinuum. And then typically in AGNs, they live in complicated environments, in host galaxies that have dust, stellar emission, many other phenomena that swamp and dilute, especially when you move to fainter states, dilute the emission of the motion. So a more historical introduction about the look for accretion states in AGN. I always show this result because this is pre-unified model. So this is a paper from 84 with observation from La Palma. And in this paper, Penston and Perez, they were discussing this curious object, 4151, which show in a period of 10 years the disappearance of the broad component in H beta and the blue continuum. No? So they were saying, okay, maybe the CEFCA2, CEFCA1 dichotomy is related to some evolution of the central engine of these objects. So maybe type 2s are just AGNs in which the nucleus has switched off. They were proposing this, and this lived for a short time because then the discovery of broad lines in polarized light in type 2 AGNs lead the way to the unified model, in which the differences between type 1s and type 2s was interpreted in terms of orientation and not of evolution or evolution of the central engine. No? So in the unified model framework, there is a component called the torus that hides the black hole and the region where the broad lines are formed. Those are the red spots. It hides the view for certain viewing angles. So if you are looking at the system from a pole-long direction, then you can see the accretion-disc and the broad line region, and you will have a type 1 AGN, no? With the broad lines and all the well-known phenomena. If instead you're looking at the system from an edge-on direction, the torus will block the view to the broad line region and the accretion disk, so you won't have the blue continuum, the broad component in the permitted lines, but you will still see the narrow lines that comes from gas that it's further distances where the torus is not blocking them, no? And you will have a type 2 spectrum. So this was published in 93 and it was very successful for maybe 20 years. And it was the interpretation, the view that was more common. Then to complicate a bit the picture, in BPT diagrams, you also distinguish between ciphers and liners based on the excitation of the lines. So even among the type 1s or the type 2s, you have differences based on the ratios of the narrow lines in the spectrum. For example, in ciphers, oxygen 3 lines are much more intense. In liners, the high-ionisation lines are lower intensity. So this created a very complicated picture with taxonomy, many classes, many classes that come from the optical properties of the spectrum, and this was hard to interpret. Then, in the last maybe 10 years, with the surveys that have that cover the sky with very nice time frequency, the the number of objects that behave like the first one that I showed, 4151, changing loop quasars, started to grow. So now we know that that object that was transitioning from one type to another was not rare, but it's a quite common phenomenon in the universe. So these are systems that in a period of a few years, they transition from a system that doesn't show the accretion-disc continuum and the broad lines to a system that show a prominent blue continuum and the broad lines in the spectrum. So these, there are also objects that have gone back and forth. So they were type 1s, so they were type 2s, they became type 1s for a period of time, and then they came back to type 2s. So they started to challenge the unified model interpretation, because you can't change the orientation like this so easily, no? There were there system also that show very high ionization lines that change from the type 1 to type 2 period. And this cannot be explained, for example, if you have like a cloud crossing the line of sight with the torus, because the time scales for a cloud emitting in the infrared to cross your line of sight is much longer than the time scale of the transitions that we are detecting. No? So this challenged the interpretation of the unified model and demanded a more accretion-oriented interpretation. There is also an interesting behavior that you can see in changing loop quasars. It's that there is if you measure the optical to X-ray slope and you compare that with the Eddington luminosity, the systems tend to have above the 1% Eddington, they show a softer when brighter behavior. This means that the optical to X-ray slope becomes softer when the system becomes brighter. But below the 1% Eddington, the systems are harder when brighter. So this means that the slope becomes harder when the system becomes brighter. This is a well-known behavior in X-ray binaries. So seeing that in changing loop quasars suggests that a similar phenomenology would apply. And it's also against the crossing line of sight absorber, the harder when brighter, because the spectrum, if you have obscuration, the spectrum becomes dimmer when it's absorbed. So it's harder because you have the absorption of the cloud crossing the line of sight, but because it's absorbing, it should become fainter. So if you see that something in the X-rays become harder but brighter, it cannot be absorption. So this suggested that we should develop or look for a similar hardness luminosity diagram for AGNs. There was a very nice attempt by Cording and collaborators in which they tried to build a similar diagram for quasars. So they are taking Sloan quasars with X-ray and radio information, and then the idea is that you cannot follow the evolution of one system, but you can use the statistics to be the longer time scales. So if you have a large sample, you will expect that the different systems will cover all the states in the diagram. Then they represent these quasars, so they show here the luminosity of the quasars against the disk fraction, and the disk fraction here is based on the optical colors, no? So for quasars where the AGN is very dominant, you are not severely contaminated by the galaxy, and you can do this. And then they come to the conclusion that when they compare the distribution of sources with the radio loudness, so the ratio of radio to optical radio, they find that systems that are closer to the hard state, they are more radio loud. So systems where the disk is less dominant, the jet is more dominant. And this is something that was expected. So this was a very nice evidence that maybe there is a common phenomenology. There are two problems in this diagram. One is that the luminosity here is not in Eddington units. So this means that if you take black hole masses from 10 to the 6 to maybe 10 to the 8, 10 to the 9, this is going to introduce a vertical scatter of 2-3 orders of magnitude. So if you want to recover the nice Q-shaped diagram, this is an important problem. The second problem is to include in this description fainter systems, because when you go to fainter systems, you cannot directly access to the emission of the disk, and then you cannot populate the tail of the cube. So you get with a amorphous O diagram, but you're missing the tail. So they did include some liners, but here they are using a prescription based on the H beta emission to put them in the diagram to be compared with the quasars. But the methodology is different between the sample and the sample. So we wanted to solve that problem, and then we implemented two different things. So first we started with a sample of 170 AGN observed by Spitzer. That was, most of them are in the 12 micron sample, but we completed that with more spectra in the literature for low luminosity AGNs that are underpopulated in the 12 micron sample. So for these systems, we collected the stellar sigma from databases, no? From Hyperlida and other databases. Because the stellar sigma, is giving us information about the black hole mass. So we can correct for the unknown black hole mass in the population. This is it's the famous M sigma relation, and it has not a small scatter, but still 0.3 dex is much better than the 2-3 dex that we had before. So we get the black hole masses from the sigma, and then we use the infrared lines to recover the information on the ionizing content. So in general, not only the infrared lines, but the optical lines, the ionization potential of these lines, of the different species of the different elements, are mapping the shape of the continuum emission in the part where the hydrogen is absorbing the continuum emission. So the extreme ultraviolet is invisible to us, but the ionized gas is reprocessing the emission of this continuum. And if you measure the lines and you establish the diagnostics, you are able to recover the shape of this continuum, at least to a first degree. So the idea is that we cannot see the disk directly, but if we are using lines, for example, like oxygen 4 or neon 5, that are close to the peak of the disk emission, we can infer if the disk is more dominant or less dominant in those systems. Why in particular we focus on infrared lines? Because two big advantages: the obscuration, so they are less affected, much less affected by obscuration, especially the lines in the mid-infrared. But there is also another big advantage, which is the temperature. So the optical lines forms in levels, in energy levels that are relatively higher, high energies. So to populate those levels, you need the gas to be at a certain temperature. And the emissivity of the lines, of the optical lines, like oxygen 3, the optical, depends very strongly on temperature. So if you are close to 10,000 Kelvin and you move a little bit in temperature, the emissivity of the line can change a lot. So this is an extra parameter that you want to avoid. The infrared lines, they form very close to the ground level, and these levels get populated very easily, so at very low temperature, and this means that the emissivity of the infrared lines is flat. It's almost flat with temperature. So those are 2, neon 3, so this is the big advantage. And also in the infrared range, you have lines that cover very different ionization potentials and very different densities. So you have tools to develop diagnostics that trace very different conditions. So in this case, to maximize the statistics, we are using oxygen 4 and neon 2 lines from Spitzer for this sample of galaxies. So what is the idea here? Imagine that you have an AGN, you have the accretion-disc, accretion disk is ionizing the gas, and the accretion disk is very prominent in the spectrum. You are missing part of this. I mean, this is an exaggerated picture, but you are missing this because you don't have access directly to the extreme ultraviolet continuum, but the presence of this disk will ionize the gas, and then with your favorite telescope, you will see very, very intense oxygen 4 emission, as compared to low ionization transitions like mu, because of the disk. If you have another spectrum without the disk, with a following power law or whatever you want, this physically means that you have a truncated disk or a cold disk. You are missing the innermost region of the disk, so the gas is ionized, but it's less ionized, and in the spectrum you have a fainter oxygen 4 as compared to mu. So based on this, we built the luminosity-excitation diagram. This is a representation of the luminosity in Eddington units. So we are normalizing the luminosity of all the galaxies in the sample. And in the horizontal axis, we built basically a line ratio that is designed to be representative of 1 minus the disk fraction, following the same analogy of the hardness intensity diagram. So this is a ratio of neon 2 over neon 2 plus oxygen 4. If the disk is very dominant, oxygen 4 will be intense, and then objects will be on the left side of this diagram. If the disk is very faint, then oxygen 4 will be small, and this will move to unity. No? And then for the luminosity, again, to maximize statistics, we are using the luminosity of the lines normalized by the Eddington luminosity based on the black hole mass of these systems. We could use here the X-ray luminosity, but then the sample will be a bit smaller, so that's why we use this one. But we compare this normalization with volumetric measurements for specific objects, and it matched very well. So basically here, you can see that we can recover the Q-shaped distribution that we were discussing above. In red, you have the cipher 1s. In green, you have the cipher 2s. In pink, you have the hidden broadline cipher 1s. So these are the systems in which the broadlines are detected in polarized light. So it means that they are cipher 1s, but they are obscure. And then the liners are shown as the blue circles. So these are the liner is based on the BPT classification. Most of the liners are low luminosity AGNs, but not all of them. So I will explain this a bit later. Basically, most liners are low luminosity. So you can see that liners accumulate in the tail of the Q-shaped diagram. Then the red symbol, the cipher 1s, tend to be more on the left side. Then the symbols are color coded with the radio to X-ray ratio. So this is a proxy for the radio loudness of these systems. So darker means more radio loud. And you can see that the symbols that are in the tail of the Q, they are darker, as compared to symbols that are in the rest of the diagram. No, we don't have the information for all of them, but in general, you can identify that. So another important thing, so yes, it's the Q of the diagram. Another important thing is that the transition from the 1% Eddington transition that I was discussing before in X-ray binaries, here it seems to happen a little bit lower, between -3 or maybe -2.5. So apparently the Q here in this diagram, it's a little bit lower than the other one. An important thing is that we don't see any system here, and there is no bias against that. So the bias should go on the opposite direction. So imagine that you have a cipher object that has a disk, but it has low Eddington. Then you would detect a relatively strong oxygen 4. There are no systems like that. There are no systems at low Eddington that have a strong oxygen 4 emission compared to neon 2. When you go below this line, all systems have very faint oxygen 4 emission. And then we compare with photoionization models for the horizontal axis. with the same two spectra, so with templates that include accretion-disc or they lack an accretion-disc, and the prediction for those models, the prediction of the Lyman hardness is called this indicator, no? The nu2 over nu2 plus oxygen form. The prediction from photoionization models, when you include the disk, is that depending on the parameters you use in the photoionization simulation, you can cover this range. But if you remove the disk from the photoionization simulation, even if you increase the density of radiation, there is a hard limit around these values. So even if your spectrum is more luminous, or if your gas cloud is closer to the ionizing source, if the spectrum doesn't have the energetic photons from the disk, you cannot make oxygen 4 to become brighter compared to nu2. So from the same distribution, we use a 2D Gaussian kernel to reconstruct the 2D probability distribution for the sample that I'm showing there. It try to identify where are the maxima or how is the distribution of the different spectral types. And here we can associate different spectral types with the different accretion states that I was discussing at the beginning. So CIFAR1s and a large fraction of CIFAR1s, hidden broadline CIFAR1s, they accumulate in the upper left side of the diagram, where the presence of a strong accretion disk is expected, and then you see a strong oxygen 4 emission. So this is associated with the soft state that we know from X-ray binaries. Then in the tail of the queue, you have a lot of liners that are radial out, and they have very little disk emission, as inferred from the oxygen 4. So this is the hard state. It's mostly dominated by low luminosity AGNs. Most of them are liners, not only. And then you also have liners that are up there in the intermediate state. So the intermediate state is the transition between these two. It is interesting that in the intermediate state, we find like half of the CIFAR2 population. So this means that the CIFAR2 population shows like a kind of bimodal distribution. Some of them look like obscure CIFAR1s. So these are the sources that are in agreement with the unified model. So maybe if you observe them with deeper polarized light observations, you recover more and more hidden broadlines. But the other half of the population, they have relatively faint oxygen 4 emission, meaning that the gas clouds are not seeing a powerful accretion disk. And they are together with a part of the liner population. Another thing that we can do, so we cannot track the evolution of an AGN across the whole cycle, but what we can do is to collapse the cycles of the X-ray binary population and see if they look similar to the diagram that we got. So here what you have is a compilation of different outbursts of different X-ray binary systems. The vertical axis is in the luminosity in Eddington units, and then it's the disk fraction on the other axis. So this vertical line here is because the disk component cannot be detected in the X-ray spectrum. That's why they are exactly at 1. And when you plot all the objects together, you recover something very similar that we are seeing in the X-ray population, in the AGN population. Of course, there are systems. So here there are uncertainties in the distances that translate into uncertainties in the vertical axis. So maybe some of the systems here should be higher, but overall the distribution is very similar to what we got. And then when we compare it with the result that we had before, we were very happy. So we find that the analogy is very aligned. No? Here the gray area, it's the same. So it's the same kernel probability distribution, but obtained for all sources when they are weighted by the radial loudness. So if I take into account all sources, but weighted by the radial loudness value, they concentrate here in this part. That confirms that radio loudness happens when the disk is less important. Some comments. This is not accurate for single sources in the sense that the disk can vary and the narrow line clouds are very far. So if you see one system that it's particularly radio loud, like 3C273, but it's in the disk dominated region, this doesn't mean that this does not apply, because the disk and the narrow line clouds are at very different distances. So individual sources might not fall in the category that you think they should, but the overall population follows the distribution. Then, so the question is, if we can detect state transitions, and what is the role of changing loop quasars? Just as an exercise, I plotted some changing look that are in the sample, where they are in this diagram, and this was not very conclusive. So I can say that they are not here in the tail, but apart from that, they seem to be somewhere in the middle. So changing loop quasars doesn't seem to be particularly happening in a particular place. But again, the broad line region is something that is much closer to the nucleus, and the narrow line region is much further away. So you expect the narrow line to respond at much longer time scales than the broad lines. And there is a hint that there is a connection with the host galaxies. So now the symbols are color coded by the star formation rate, and this star formation rate is derived from the PAH emission at 11.3 Mach. So the PAH tend to be weaker or destroyed by the AGN, so it's a tracer of star formation rate that is not contaminated by the AGN. And it comes from the same aperture of the Spitzer spectrum. So it should be tracing the star formation rate in the region where the infrared spectra were measured. Here you can see that in the tail of this cube, these galaxies are typically elliptical. So these are M87, Sombrero galaxy. These are the kind of galaxies that populate the tail of this cube. Sieverts have intermediate star formation rates. They are not particularly strong star forming system. They tend to be spirals with a bright nucleus. But then the liners that were in the upper side of the diagram, the galaxies that are here, so systems that are at high Eddington, but they don't have a strong disk, these systems show very strong star formation rate. So these are typical mergers, NGC 6240. So those kind of galaxies fall here. There could be some contamination of the neon 2 line because of the star formation rate. So maybe some of these blue points should be moved a little bit to the left. I don't know. But overall, it seems that the kind of galaxies that are there are different, and the nucleus, the AGN nucleus, have different properties as well. So this is a very interesting connection that should be investigated further. And then I check for the black hole masses if there was some bias maybe, and not. So the symbols are now color-coded with the black hole mass derived from the sigma or from dynamical measurements if they were available. And there is not a particular massive black holes are not in a particular region of the diagram. So what is the next step? So the next step is to move from Spitzer, that's the data I showed, to James Webb. So during my PhD and later, I was working with a sample of low luminosity AGNs that I extended during my research. And these low luminosity AGNs, they are scattered along the tail of the cube in this diagram. No? So based on studies with high angular resolution, I can isolate the emission from the nucleus of these galaxies. No? And I can study in more detail how is the shape of the ionizing continuum when the disk is not there. So these systems, they tend to show like a broken power law distribution, most of them. So the black dots are high angular resolution measurements, so lower than 1 arcsecond. So these are measurements that have very little contamination from the host galaxy. The gray spikes are contaminated by the host galaxy intentionally, so these are large aperture measurements. And X-ray measurements are not high angular resolution, but in such high energies, you don't have strong contamination from the host. So this system tend to show a flat, more or less flat spectrum with a turnover at a certain frequency, and then a power law that falls down, then probably the inverse quantum emission that it's represented by a different power law in the optical to X-ray. So these are the typical, this is the typical shape from compact jets. So this means non-thermal emission from electron population that in the lower frequencies is self-absorbed, so it's optically thick. The flat part is optically thick. Then the emission becomes optically thin at a certain frequency, and then you see the steep power law from the optically thin emission, which is the more energetic emission from the newest or more energetic electron population. So then we start thinking, okay, this fits with the schema that I showed before. These systems are in the tail of the tube. The disk is not important in them. And then when I look with high angular resolution, the continuum looks like thermal. So this is what we can describe from the mid-infrared to the ultraviolet. But then we have a problem because there is a big gap here that we cannot cover with direct observation. So that's why I was saying before that we have to use the emission lines, because about 2000 Armstrong, then hydrogen in the host galaxies and also in our galaxy kills all the radiation. So you're missing the information on this part until the X-rays. But we can do, I'm going to skip this, it's too technical, but we can use the lines, emission lines, to recover the information in this part. The same technique that I was describing before. So for example, if you have a more disk-like continuum or a more inverse Compton jet-dominated continuum, the lines that are mapping that energy range are going to respond differently. So from the different line ratios, you could infer if your shape is steeper, flatter, or softer. No? That's the idea. Before we had a Spitzer, so these systems are the faintest ones. So when you go to Spitzer, you barely detect emission lines, and especially high-ionisation emission lines that are the ones you need to cover this more energetic part. They were extremely faint in Spitzer. So that's why we were working with oxygen 4, because it was basically the only line that for the low luminosity AGN population had enough statistics. This was like this, but now with James Webb we can do much better. Because with James Webb you have access to all for example, all the transitions in blue are transitions with more than 54 electron volts ionization potential, and that means that they trace very well the part of the accretion disk. So now we have access to neon 5, neon 6, and many others that are fainter in this figure are didn't indicate. But this allows you to establish and to analyze more different diagnostics. So in the literature, you can find diagnostics that exploit the neon 5 to, this is one of the most famous ones probably, neon 5 to neon 2, neon 3 to neon 2. And on top of this, you have photoionization models for AGNs, photoionization in green, star formation in blue, with extreme populations, if you go to this part. And then also shocks. Shocks create kind of, if you add shocks to the AGN photoionization, you will create a tail here that more or less describes part of the cipher population, but it's what it's shown here in the gray points. So this is probably one of the most famous diagnostics nowadays with James Webb. So what we did is to use models, but models specific for low luminosity AGNs, try to predict how is the line ratios predicted by this kind of continuum. The blue line, it's a model for a classical CEFCA1, no? a prominent accretion-disc dominated AGN. And then we use simple broken power law based on the ACD of the Sombrero galaxy, and then also a more model based distribution, that is the pink one, which is based on ACD fitting from Ivan Lopez paper, but it's in agreement overall with the shape of Sombrero galaxy. No, it has a very steep slope from mid-infrared to the ultraviolet, and then a steep increase from the ultraviolet to the X-rays. So it's very different from the accretion-disc emission. This is a work I'm doing now with Michal Azaria, which is a postdoc in Física. And then the same diagram that I showed before, the prediction of these models for the same diagram I showed before, is the following. The blue grid corresponds to the disk-dominated models. The pink grid is the model based on the ACD fitting or low luminosity AGN. The green grid is based on the Sombrero galaxy. Then the purple squares are James Webb measurements for CEFCA galaxies. The black ones come from Spitzer, and the orange one are from a sample of low luminosity AGNs. Some others from a few ones that have been published in the literature. So if you compare this with the models, you can see that the grid of photoionization models for the disk emission, different ionization parameter and different densities, they map very well the distribution of excitation that you see in the CEFCA galaxies. And the models specifically dedicated to low luminosity AGNs, they also reproduce very well the location of the low luminosity AGN sample in the distribution. There are a few rogue objects. This one here is a low luminosity AGN in terms of absolute luminosity, but in Eddington luminosity is not a low luminosity AGN. So this is an object with an intermediate mass black hole. So it was classified as a low luminosity AGN because it's not very luminous, but it's high Eddington. So it should have a different symbol. And this one is another where maybe shocks are important. So it's falling apart in this part of the data. Compared to the models I showed before, if you look at the numbers, the shock models, the distribution that I was showing before that generates a tail here, it's following this distribution up there. So the shock models plus AGN photoionization does not reproduce this region of the data. And instead, only with the photoionization predicted by a compact jet continuum can reproduce very well the distribution of the low luminosity AGN line radius. With James Webb, we can explore more interesting line radius that were too faint and not detected by Spitzer. For example, Argon 3 to Argon 2 is very good at separating in the horizontal axis low luminosity AGN CEFCA galaxies. And another interesting thing is that if you go to a ratios of very high energies, if you go to the neon 6 to neon 5, then the spectra start to become more simple. So it's like this shape, the disk and the jet, they are converging to a more common slope. I think this is reflected by this rating. So if you do neon 5 to neon 2, yes, CEFCAs are much more powerful. But if you compare two high ionization lines, then low luminosity AGNs are very comparable to the excitation level that you get in CEFCAs. And this is a very interesting result. So based on simple models like this, now I run another set of photoionization simulations with the blue the green and the red lines. And if I put them in a similar diagram, as I showed before, I can reproduce the three main accretion states I was discussing at the beginning. So red models accumulate in the upper left side of this diagram, where the disk emission is prominent. And in the continuum emission, you are putting a prominent accretion disk plus this soft excess. No? Then low luminosity AGN models, if you just use the slope that you see here in blue, you get models that if they are very luminous, they can get here, but they cannot move too much to the left. And if they are faint, they will go to the tail of the cube. And if you have a flatter distribution, those models are going to be there. So we interpret this as a confirmation that the different excitations that we see in the alien population is connected to the appearance and disappearance of the accretion disk, depending on the accretion state. So this is the evolution that we think systems should have in this kind of value. So this is basically everything. I hope you enjoy the discussion of the accretion states on supermassive black hole. I think this is a nice exercise to look for a more accretion-oriented classification of AGNs. So instead of that based on many classes from the optical spectrum and with many different properties, that it's very confusing and hard to explain, especially when you talk with non-AGN people, to something that is more physically connected to the process of accretion that we know they work and how they work in the X-ray binary world. And yeah, I hope you learn something from nebular lines to record the primary ionising continuum. So thank you very much.
Thank you very much, Juan. Super nice presentation. Let's have some questions.
I did not totally get it why there are no sources located at the bottom left side of the diagram.
Yeah, so in principle they could. So if the accretion framework that I described for X-ray binaries would not be happening in AGNs, you would expect that there could be sources there. No? So imagine that if you put a point here, that source would be an AGN with an accretion disk, luminous accretion disk that is exciting the oxygen-4 in the clouds around, but it would be at low Eddington rate. So it would be accreting at a low percentage of its capacity. So that can exist. And if that system would exist, I would detect it because it would have bright oxygen-4, but they are not there. So the fact that they are not there means, or I interpret that as a confirmation that below a certain accretion ratio, there are changes in the structure of the accretion disk. So those systems don't disappear. They are not here because when you go below a certain Eddington, the disk vanish and the jet takes control, as it happens in the X-ray binaries. By the way, I didn't say it, but the overall idea is that this is a heating and cooling cycle of the corona. So you have the corona around the black hole. When the corona is very hot, you have a powerful jet. But when the accretion processes start to emit a lot of ultraviolet photons cool the corona through inverse quantum processes. When you cool the corona, you lose the jet. So that's why when you get a more prominent disk, you get a less fainter jet. And then the opposite happens when the accretion processes stop or decrease, then the corona starts to become hotter and hotter, and then the jet reappears.
I have a question. If we assume the physical mechanics behind the state transitions in black hole X-ray binaries and the state transition in internal agents are the same, I wonder if the timescales match the
No, they don't match. This is one of the interesting questions. So if you scale the time scale of the chain loop transitions to the X-ray binary world, it's a too short time scale because it's years. So in stellar mass black holes, it's too short. So, but the problem here is that the physics of the accretion disk are not the same. The physics of the jets scales with mass, so it's much easier to understand. But the physics of the accretion disk doesn't, because the accretion disk in AGN it's pressure dominated, I think, while in X-ray binaries temperature is dominated by other processes. So the mechanisms that trigger the instabilities are expected to be different because the physical conditions of the disk are different. So I think there are different accretion states. I think there are transitions, but the mechanism that trigger the transition it is completely different. It might be completely different. And this is an interesting question to understand. What is the equivalent of the changing look phenomena in X-ray binaries? We don't know. Changing looks tend to be here, and but they are so short that it cannot be the whole cycle, no? Because in a few years you have a type 1 that comes type 2 and then comes back. So we don't know.
I have a question. Actually, I have many questions, but I'll go only for two. One is, how do you know for sure that these high-ionisation lines that you use, like Tritium-4 and Neon-5, come from the AGN? Because they can also be produced by tidal reduction events, for instance, like very energetic processes, like TVEs.
Well, TVE is forming the same phenomenology. It's forming a disk and the same phenomenology applied. So I haven't dig too much into TVEs, but the groups that study TVEs, they follow this scheme. So if you have, so in a TDE, you don't, the material is disrupted and the densities are very high. So you don't get to see I think you don't get to see the narrow lines here. Because these lines, when the density is very high, they are collisionally de-excited. So to see these lines, you need gas that is at 10 to the 3, 10 to the 4 particles per cubic centimeter. If you have a tidal disruption events, you typically see the helium, the hydrogen lines, and then it's gone. So it's difficult. I have to check, but I think there are no studies detecting these lines in tides. They cannot come from star formation because they are too energetic. So this is a stellar template, and then stellar populations, they have a strong edge here. The second ionization edge at 54 electron volts means that the opacity for the stellar atmosphere is super high above this energy. So the stellar population can be very energetic below 54 electron volts, but then they drop. So when you are looking at lines that are above 54 electron volts, oxygen 4, neon 5, etc., and then you do a ratio compared with other lines that are here, then AGNs are much more powerful. The ratios for AGN systems are much more high, because in AGNs you have a power law here that it's not dropping at that level.
And my other question was, it's very nice that you connect stellar mass black holes and AGN now, like supermassive black holes, but you know there's an intermediate regime, or there should be, of intermediate mass black holes. So could this be applied also to this lower mass AGN to complete the whole mass scale?
Sure. In fact, this is in one of the diagrams. There is an intermediate mass black hole. This one, the one I said, it was confused by a low-luminosity AGN. It's actually so this one is 4395, the famous one. So it has less than 10 to the 42 erg per second in volumetric luminosity. So it was automatically entered the sample of low luminosity AGNs. But when you look at the spectrum, and it's full of neon 5, neon 6, magnesium 7, it's super energetic. It's full of lines. So yeah, it fits totally in the spectrum. It is in the CEFCA So it's compatible with a source dominated by a disk.
Online. Are there any questions online? Okay. Antes no lo oíamos, pues.
Maybe I can open
That's-
the chat.
Yeah, exactly. Okay, no, mira, no. Okay. Any other question? Otherwise, fun to be here the whole day. I'm not sure until what time in the afternoon, but there are still free slots available. It was stop cooking. So let's thank him for coming here and giving this nice presentation. Thank you.
No, mira, pues,
No, 35.
Okay.